On to problem 3, we have the question, given that the theoretical reaction below was found to be second order and bimolecular, provide a rate equation law for the reaction. Okay, so a couple things to define right away. These key words that give us the answer to the problem: second order and bimolecular. Bimolecular means there's going to be two concentrations. So based off of this equation here, which gives us rate laws, that means there's going to be A and B concentrations instead of just one. Because really this rate can be, this is a basic equation. This can go on to different depending on how many molecules you have. This is a bimolecular equation. If it was a monomolecular, you just have the concentration of A raised to its coefficient. The coefficient, that's just the number coming from this reaction here, the number in front of it. So this lowercase a. So if this was an actual equation, let's say it was H2 plus oxygen to give us water, we'd have to balance that equation first. We have 2 on this side, so really we'd end up with way too many oxygens on this side since we have 2 and only 1 on this side. So we'd have to balance this. We can balance this by putting a 2 in front of the H2O. Now we have 2 oxygens, but 4 total, because 2 times the 2 we have here gives us 4. So we'd have to put another 2 in front of the H. Now we have a balanced equation. But now we have these coefficients, or numbers we're multiplying to our actual molecules in front of them. So this 2 over here is the same thing as that A down there. And that goes into our rate law. All our concentrations are raised to the power of that coefficient, or that number in front of the molecule. So if we had a monomolecular, you just have an H2, maybe just splitting up to 2 individual H's. A weird reaction, but it's possible during certain conditions. So this would be dependent on just one molecule. It would be mono. So here we know that we have these 2 molecules, A, B. This rate law we know is just like this one up here that we first started out with. It has 2 molecules. It's bimolecular. We could have tri with 3 things, and we could throw in a C if we wanted to, raised to its same thing, raised to its coefficient. But since it's bi, we know that right away we have a rate law of something like A times B. But we don't know is their coefficients. Looking at this, we know that A is the same thing as this molecule, and this is B, so we can plug those into our concentrations. So we have A to the B times C to the D. We don't know coefficients, but we do know that our reaction is second order. Second order has to do with these coefficients, the things that we are raised to in the equation. So like you see this, the lowercase a's give us the rate laws, and they're the same thing as the coefficients over here, as we just said. Now to figure out if it's second or first order, we add them together. So really our order of the problem is the same thing as A plus B, so on and so forth, depending on how many coefficients you have. And we know it's second order, so second order means that there's 2. So we know A and B plus B equals 2. So these things have to add up to 2 total. And from our equation, we know that their coefficients are 1, because when something doesn't have a coefficient, we always can assume it's 1 times that. Since they're both 1, they add up to 2, and that'll fit into our second order. If it was third order, we would have to assume that one of these was raised to the second power, because it needs to add up to 3 total. And if it was first order, we would assume that it's just dependent on one of these. And let's not forget our coefficient, this kr over here, which is our rate constant. Just a constant number that would be found experimentally.